Okay, since it is already 3 o'clock, let's get started with start at the TA session. So, welcome everyone to week 6 of the course Optical Spectroscopy and Microscopy, Fundamentals of Optical Measurements and Instrumentation. I am Arjun, and as you might already know, for the past 5 weeks, I am your TA for this course. So, we are right now we are halfway through the course where we are at week 6. So the routine for this course week's TA session will be simple, where we will be going through a brief recap of whatever happened in the course lectures for this the lectures for this week, and followed by that I'll be discussing some of the sample problems which I have curated on my own, and after that we'll be discussing some of the previous week's assignment session. So the previous week we discussed about week three's assignment. So following that, we'll be discussing week four and almost half of week five. The rest of the week five and week six I will be covering in the next week's TS session. So we'll get started directly with the week's recap. 1 second. Huh. So yeah, so week six's content mostly focused on lasers, and even in lasers particularly, the week six lectures focused on continuous wave lasers, where we saw about different types of lasers and how laser basically happens. So laser, in short, abbreviated, stands for light amplification by stimulated emission of radiation, as you might already know by now. And we all saw that how in the previous 5 weeks we were building up the process of absorption, emission, and fluorescence emission, which will all contribute to the process, finally contribute to the process of lasing. And from this point onwards, we'll be looking at different types of lasers, how different types of optical components will be coming together to form a microscope. So as a result, we started with the introduction of lasers, and we saw how in order for a laser to function, we need some process called as population inversion. This is a process where the number of electrons in the excited state is more than the ground state, and we were seeing at different levels of lasers, mainly 2-level lasers, 3-level lasers, and 4-level lasers, and we were also looking at certain examples of lasers in each of these categories. We started with a 2-level laser where we further started to explain the rate of uh, ob- excitation and emission using quantum mechanical phenomena, and we came to a conclusion in 2-level laser where how how or why we can't have a 2-level laser, or why it can't be as efficient as a 3-level laser or a 4-level laser. So after this, we went on to discuss about 3-level lasers, where we took the example of ruby laser, where ruby uh, ruby is mostly alumina, which is doped with chromium ions, which has a excitation of which is an emission of approximately 694 nanometer, and it has a lifetime around the order of milliseconds. In the ruby system laser, we saw how it has a how it mostly functions in a 3-level system component, where you have your um, absorption process happening to the excited state, and in addition to that you have a radiative emission happening from the excited state to a ground state, and in between both of these states we have a metastable state, where you have a fast internal conversion non-radiative process, and from the metastable state we have a emission which functions as the lasing medium. So through mathematical processes, once again we saw what is the criteria for this population inversion to happen, and we basically saw that the rate of this non-radiative relaxation must be greater than the rate of this spontaneous emission from the metastable state to the ground state. So in that case you will have more number of electrons in the metastable state, in which case your population inversion happens. And following that, we also saw more about the 4-level laser, where we took the example of your helium neon laser, which is a gas laser, which emits at a wavelength of around 632.8 nanometer, where the helium neon laser mostly functions as a result of the collision of helium and neon ions. And in the 4-level laser, we also saw about how there are four different levels, where your lasing medium consists of two different levels which are not part of your excitation or your main emission levels. Instead, the lasing medium only consists of the neon medium, where you have non-radiated relaxation happening from the excited state to a first metastable state, and followed by the lasing medium, which where the second metastable state de-excites to the first metastable state, and where another non-radiated relaxation happens to the ground state. So in both these cases, we saw that the rate of the non-radiated relaxation to the um, upper metastable state should be higher than the spontaneous emission rate to the ground state, in which case your population inversion can be achieved. So these were the main concepts that we discussed with the lasers, and apart from that, we discussed additional small concepts such as coherence as well as your spectral brightness. So coherence would judge the ability of a laser to be ability of laser to be consistent at two different time points, and with respect to coherence, there are two different concepts, mostly your spatial coherence as well as your temporal coherence. Your spatial coherence will be associated with a parameter called as your coherence volume, whereas your temporal coherence will be associated with your phase differences between your laser at two different time points. But on the other hand, spectral brightness is used to judge the power of a laser, where spectral brightness will be the power of a laser. Sorry, spectral brightness is a property used to adjudge the um, power of the laser with respect to the region in which it emits. So it's basically a measure of your power of the laser with respect to this excitation wavelength. So it has units of around watt per nanometer. So these are all the general concepts that were discussed in week 6. So if people have any doubts with us regarding to these concepts, please feel free to ask. Even we can maybe have 2 to 3 minutes discussion of these concepts, after which we can go and discuss the sample problems. Okay, if there are no questions, we'll go on to the discussion of problem statements. So the first question is, why is a four-level laser system generally more efficient than a three-level laser system for achieving population inversion? So uh, we have came to know from the concepts that a four-level laser system is generally more efficient than a three-level laser system. So why is it so? It's a MCQ question, and the options are option A, it uses photons with higher energy. Option B is the low laser level is quickly depopulated to the ground state, making inversion easier to maintain. Option 3 does not require a pump source. Option 4, it only works with gas phase molecules. So the answer here is option B, just the just the low laser level is quickly depopulated to the ground state, making inversion easier to maintain. So we all saw from the this thing that the efficiency of the laser mainly depends on two parameters: the number of photons in the laser and the pump, and also depends on the rate of the non-radiative relaxation to the rate of the spontaneous emission. So in whichever laser the spontaneous emission is faster, the efficiency will be higher. So in the four-level laser system, the lower laser level is quickly depopulated, as in the spontaneous emission is faster. So this makes inversion easier to maintain. Yeah, so the inversion is for longer, so it makes the four-level laser system more efficient than a three-level laser system. So the second question is purely theoretical. The laser gain in a medium must overcome what to reach the threshold for lasing? So the laser gain in a medium must overcome what to reach the threshold for lasing? And the options are the weight of the gain medium, the total round trip losses in the cavity, the frequency of the pump, and the refractive index of the solvent. And the answer here, we all know that it is related to the round trip loss, because there are two mirrors and all the mirrors will not reflect the lasing medium completely. So it will undergo some loss. So minimizing the loss will help in overcoming, like achieving a more gain. So the option is option 2, total round trip losses. So question number 3, to generate a laser pulse in the femtosecond range, a laser must have what? So should it have a frequency, a very broad bandwidth, a very narrow bandwidth, a low pump power, or a mechanical shutter? And this is the answer to this question is bandwidth, obviously. So the higher the bandwidth, the lower the laser lifetime will be. Sorry, the broader the bandwidth is, the lesser the lifetime will be. And this question you might have already come across. So the Einstein A coefficient for spontaneous emission is related to the B coefficient for stimulated emission by a factor proportional to what? Frequency, frequency square, frequency cube, or reciprocal of frequency? And the answer here is frequency cube. The next question, in a semi-classical treatment, light is treated as a wave and matter as a quantum system. In a fully quantized treatment, what is what? So matter as a classical particle, Einstein coefficients are no longer used. The uncertainty principle is ignored. Both light and matter are treated using quantum mechanical operators. And you can kind of read from the question itself, and the answer would be obvious, which is the light and matter are treated using quantum mechanical operators. So this is a numerical problem. Um, so we have to calculate the ratio of Einstein coefficient for spontaneous emission to the coefficient for stimulated emission for a laser occurring at 500 nanometer. and we have to express the answer in the order of 10 power minus 13 joules per second per meter cube. So the only parameter that we have got here is 500 nanometer. So we have to figure out how to make use of it as well. So the problem, the way to solve this is simple. So we just have to use a simple formula. So we already know that the ratio of A to B is given by this formula, which is 8 into pi into h by lambda cube, where lambda cube is the wavelength and h is your uh, Planck's constant, which is 6.6246 into 10 power minus 34. So just substitute all your values in this formula and like substitute our Planck's constant, which is 6.626 into 10 power minus 34, and your wavelength is 500 nanometer, which is basically 500 into 10 power minus 9 or 5 into 10 power minus 7, the whole cube. So if you substitute all these values, you will get the ratio of A to B as 1.33 into 10 power minus 13 joule into second per meter cube. And since I have asked the answer in only 10 power minus 13 joule centimeter per meter cube, the answer will be 1.33. So question number 7, uh, I think this is the last numerical problem that I've come with. So a titanium sapphire laser is mode locked and produces a pulse with a duration of 20 femtoseconds. So femtosecond basically means 10 into 10 power minus 15 seconds. Assuming the pulse is transform limited, where your delta nu into delta t is equal to 0.44, calculate the minimum frequency bandwidth in terahertz required to support such a short pulse. Yeah. So this is also a very simple problem, just simple substitution. So I have already given you that delta nu into delta t is equal to 0.44, and here I have already given the delta t, which is the pulse duration, which is 20 femtoseconds, which is 20 into 10 power minus 15 seconds. So just substitute the value delta t with 20 femtoseconds and displace it to the other side to get delta nu is equal to 0.44 by 20 to 10 power minus 15. So if you do that, you'll get the answer as 2.2 into 10 power 13 hertz. But I've actually asked the answer in terahertz, which is 10 power 12 hertz, 10 into the power 12 hertz. So 2.2 into 10 power 13 is 22 into 10 power 12 hertz, which is 22 terahertz. So the answer will be 22. So these are the sample problems that I have. So we can have a short doubt session before, after which we can move to discuss the previous um, assignment questions. So if you have anything. Okay, if there are no doubts, we'll want to discuss the assignment solutions from week 4 first. So the first question is given two sets of fluorophores with the following absorption coefficients 63,000 and 54,000 and excited state lifetime of 2 nanosecond and 4 nanosecond. Two experimenters differ in their choice of fluorophore and reasoning. So experimenter A chooses fluorophore 1 with the reason being higher absorption coefficient and higher rate of absorption at lower excitation intensity. Higher rate of spontaneous emission implies more fluorescent photons per unit time. And experimenter B chooses fluorophore 2 with the reason lower absorption coefficient implies lower intensity to reach maximal stage of absorption. Higher lifetime, which is 4 seconds, means fractions of molecules coming down through fluorescence is higher. So which one of them will be higher? Which one of them are correct here? Either experimenter A is correct or experimenter B is correct. So if we look at both experimenter 1 and 2, the reason saying, so experimenter 1 has chosen fluorophore A, which has higher absorption coefficient and lower fluorescence excited state lifetime. And he is saying that higher absorption coefficient implies higher rate of absorption at lower excitation intensity, which is totally true, because even with lower intensity, it means that higher rate of electrons get excited to the excited state, so it implies higher rate of absorption, and it also means that higher rate of spontaneous emission, so it implies more fluorescent photons per unit at time, which is why you're getting the low excited state lifetime. So which is completely true here. And on the other hand, if you take B's this thing, so he's saying lower absorption coefficient implies the fluorophore require low intensity to reach this maximal state of absorption, which is totally wrong. So from both these choices, we can see that A's choice and reasoning is correct, while B's choice and reasoning is incorrect. So the correct answer will be option B. So second question, find the excited state lifetime of a fluorophore whose rate of fluorescence decay is 2 nanosecond and non-radiative decay is 4 nanosecond. So we have the radiative decay and non-radiative decay. So we should apply a formula here saying that the uh, excited state lifetime is basically, so so excited the total excited state lifetime is tau. So tau will be represented by 1 by kt. So kt is basically k total, the total rate of transition of radiative non-radiative process. So kt will be kr plus knr. So kr is basically your fluorescence decay and knr is basically your non-fluorescence decay. You have to find the rate of both the fluorescence and non-fluorescence. So it will be 1 by 2 plus 1 by 4. So it will be 1 by 2 plus 1 by 4, which is 1 by 0 0.5 plus 1 by 0 0.25. So which will be 1 by 0 0.75, which will basically give you 1.33 nanoseconds. So the correct answer will be 1.33 nanoseconds. So FRET is a process, third question, FRET is a process in which the energy of a donor present in excited state is transferred to donor through non-radiative means to another neighbor fluorophore. The efficiency of such transfer reduces the sixth power to the distance between the acceptor and donor. If such a transfer happens between acceptor and donor, then what happens? So this is a purely theoretical question where you already know that the lifetime of the donor will not increase and the lifetime of the acceptor will increase. So the correct option is option B. Fourth question is again a theoretical question. So the eigenstate, what does the eigenstate in a Fock vector space represent? So it's related to the number of entities present in the state. It's option A. So the same question will be repeated again, I think, in the question number 7 or 8. So the So the creation operator when operates on a Fock state with energy Ek, what happens? And we all know that creations operator it does not have any physical correspondence. So option B is the correct answer. So the operator A star, where A and A star are creation and annihilation operators, operates on Fock state Nk yields what? So we all know that if Nk represents the number of particles or number of entities in the kth state. So if creation and annihilation operators operate simultaneously on the Fock state Nk, it will yield you the same Nk. So the answer will just be the number of particles in the state K. So using seventh question, using Fock states and results of TDPT, the rate of transition of molecule in an excited state is shown to be proportional to Nk plus 1. So Nk, so if we have emission and if we have this Nk plus 1 term, here we automatically know that this 1 is a spontaneous emission and your Nk is the simulated emission. So even if your Nk is 0, it means that the spontaneous emission will keep happening. So when we look at the first option, which says spontaneous emission is represented by the integer as when nk is 0 and the rate does not go to 0, this is true. And nk represents the stimulated emission as the resulting emission is dependent on the intensity of the incident or existing or interactive photons. That is also the true. And if you see the C and D option, both of them are polar opposite to A and B option, so it won't hold true. So the correct options are options 1 and 2, where your integer represents your spontaneous emission and your nk represents the stimulated emission. So eighth question, if instead of nk plus 1 in the above expression for rate, if it were to be nk plus 0, then what would happen? So if it is nk plus 0, so we also saw from the previous question that your integer value is your spontaneous emission. So if there is no spontaneous emission, then whatever emission is going to happen in that state will be because of stimulated emission. So if some electron can only emit if it is stimulated, then it will have an very infinite excited state lifetime. It can stay forever in that excited state without any perturbation. So, and in addition to that, um yeah, in addition to that, whenever you excite across a spectrum of wavelength, all the wavelengths will not pick up any signal because there won't be any spontaneous emission happening in that energy levels. So the correct answers are options 1 and 2, where the fluorophore will have an infinite excited state lifetime and the emission spectrum will be narrow. So ninth question, if the intensity of a spectrum at two wavelengths are in the ratio of 1:4, the ratio of the matrix element corresponding to the transitions are in the ratio of what? So here also it's pretty simple. So we know that the we know by relation that using this TDPT and using this TDPT we know that the intensity of the sorry yeah the intensity of the spectrum corresponds to like it is directly related to lot of parameters, and one of the parameters is the matrix element, and it varies by the square value. So so if we say R is the matrix element, so your intensity of the spectrum is proportional to R square. So here they have given the intensity has 1:4. So if you want to find, so we have to find the R ratio. So R will be basically root of 1/4, which is 1/2. So the ratio of the matrix elements will be 1/2. So the last question of week 4 will be to identify the allowed transitions among the following diagrams. So there is a common uh, concept here. So all of them have. So if we take the case of C, B, and D, all of them deal with ground state to excited state transitions, where you're having where C and B and C represent your excitation process, your absorption process, whereas your D represents your stimulated emission process, where they are given the energy as corresponding to the difference between energy of the photon as being the difference equal to the difference of the excited state and the ground state. However, if you see option A here, uh, option A deals with the transfer of energy from two different levels of excited state as well. So in the bottommost excited state, if energy of h nu 1 is administered, there will also be a stimulated emission to the ground state alongside to the excited state. So the correct options will only be B, C, and D. So I think that is all the um, assignment problems for week 4. I'll start off week 5's assignment problems as well, where we'll discuss the first half of the problems. So the first question is a theoretical problem where we can see that the vibrational energy loss associated with the internal conversion is what? So we all know that it's transferred to the vibrational energy loss is uh, associated with the transfer of your energy to solvent molecules. So the correct option is 1 here. The second question is, if we were not to use Bonhoeffer approximation, what would happen? So if we do not use Born-Oppenheimer approximation, then the electronic, vibrational, and rotational motions cannot be independently described. Only using Born-Oppenheimer approximation, we are able to relate the energies, the wave functions, as well as the Hamiltonians of your electronic, vibration, and rotational motions, as well as your nuclear spin actions, which is so these concepts are applied for the next 2 3 questions as well. So Born-Oppenheimer approximation assumes that the total wave function is represented as what? So that we all know that except for energy, all the wave function as well as the Hamiltonian is a product of your electronic, vibrational, and rotational wave functions. So they have asked for the wave function, so it will be a product. So the option will be 2, can be written as a product of your electronic, vibrational, and rotational wave functions. And here we are looking at the energy. The fourth question, we are looking at the energy. So the energy will be a simple sum compared to your wave functions in Hamiltonian, where it will be a product. So it can be written as a simple sum of electronic, vibrational, and rotational energies. So fifth question is also a very theoretical question. So the mirror symmetry seen in solution spectra, either is your excitation and emission spectra of fluorophore, is a consequence of what? And we all know that it's a combination of your Frank Condon and the Kasha's rule. And your last question for today, the emission spectra of a molecule is what? So the emission spectra is independent of the excitation wavelength, independent of the number density of molecules, is a mirror image of absorption spectra of the fluorophore, and is lower in energy than of the excitation light. And the correct option, since it's MSQ, the correct options here are options number 1, which is the emission spectra is independent of the excitation wavelength, and option 4, where the emission spectra is lower in energy than that of the excitation light. So that's all the sample problems as well as the assignment questions that I had to discuss for today. So we have time remaining in the session. So if anyone else has any doubts, the session will be open till 5. So if anyone has any doubts, they can shoot up those doubts. If no one has any doubts, we can meet in the next year session. Ideally, it's supposed to happen on 8th March, which is the next Sunday. However, I might not be available on that Sunday due to me attending a symposium which is organized for scholars. So I'll try to rearrange the class to 10th March, which will be the next which will be the next Tuesday, which is the second Tuesday from now. From uh, the timing also I'll let you know. Probably it will not be from 3 to 5, but rather it will be from probably from 6:30 to 8:30. So till then, you can have a doubt session where I can help you clear your doubts. Dimla Devi, the session is actually open for doubts. If you have any doubts, we can ask. Um, okay, if there are no doubts, I'll see you guys in the next session. Um, Probably the date and time might not be accurate, but I'll let the NPTEL team know when the next T session will be. Thank you.